Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to focus on benzene, which of course is an aromatic compound, and anything which would contain benzene would be considered aromatic. To be honest with you, benzene might be the most important chemical compound in organic chemistry. It is used in pretty much all pharmaceuticals, as well as many other things. It is a fundamental building block for most critical pharmaceutical products. So we're going to talk about, the 5 sections as usual: naming and writing the formulas, properties, drawing, reactions, etc. But this is very basic. Benzene and all the reactions it can do can get quite complicated, so we're going to keep it very simple here. So in terms of naming, it's pretty straightforward unless you have a benzene as a side group, which is called a phenyl. But in terms of benzene being the parent chain, the naming system might be the easiest. So for instance, when we look at this first compound here, I notice I have an ethyl group on a benzene, and it's simply called ethylbenzene. There's nothing else to it. I don't have to change it in any other way. So just like cyclic compounds, when you have one branch or a side group on a benzene, there's no location needed. It's assumed that this is in the first position. And just like cyclic compounds, once you have 2 branches, then you have to start numbering them. And this is where it can get a little bit complicated. So of course I have a methyl group here on this one and an ethyl group there. So this is either 1,3 or 1,3. So we have to follow that tiebreaker rule, where both of these are not correct. One is more correct than the other, which is we're going to give the lowest letter, which is E, the 1, and the highest letter, M, the 3. Again, this is only in a tiebreaker situation. Normally we're just trying to number things to keep the side groups as low as possible, but in a cyclic type of structure like benzene is, it really doesn't, there's always going to be a 1 something else. And I'm going to talk about that a little bit more here. Okay, so this would be 1,3 dimethyl benzene. Okay. The reason why I'm showing you the next one is for a couple of reasons. To review that what benzene looks like when you're looking at all of the atoms. So the 2 pictures above are 2 different line diagrams, which are totally acceptable. One has the circle in the middle and one has the 3 double bonds. Of course, there actually is no double bonds. If you've watched our first episode in organic, we talked about aromatics and benzene in particular, which is C6H6. These double bonds are actually 1 1/2 bonds all the way around, and the way that we normally draw it is with this circle to represent the fact that there are no double bonds, but this is a resonant structure. So here's a different way of showing it. They're showing all the atoms of carbon, and they're just using some dashed lines in between to say, these aren't double bonds, these are kind of 1 1/2 bonds. So that's one reason I have this picture, so that you recognize each carbon in a benzene can only be bonded to one other thing. So this one's bonded to a hydrogen, this one's bonded to a hydroxyl group, this is bonded to a hydrogen. Each of these carbons can only be bonded to one other thing other than the carbons in the ring. So the reason I picked this one again is to show the look of it and what it really looks like. The other reason is to talk about this hydroxyl group here. So this actually has a special name. This would be called phenol, which is a benzene with an alcohol group. It has many other names, but generally we call this one phenol. Another one would be called benzenol, is also used. But if you go to Wikipedia or somewhere online, you will see about 4 or 5 different names for it. So the OL is really your hydroxyl group. And then where it says benzene, that's the benzene. We're talking about the benzene for the rest. Or fen is also for the benzene ring. So generally when you have something more important attached to a benzene ring, the priority changes, and we don't deal with a lot of priority in our course. But an alcohol group is technically usually more important than a benzene group. It has the name fen or phenyl, and we're going to get to a couple more of those. Generally, we don't see it tested in our course, but as you move on in chemistry into university, depending on your professor, they're going to use probably one of these two names. Okay. The next one, again, has a special functional group, which we're still have only barely touched upon, which is a carboxyl group. So this is COOH. This group here, again, is a carboxyl group. And we learned in acid-base equilibrium that it is this hydrogen that ionizes in water. So it would be water here. When it hits that, it would actually pull this hydrogen off and in turn become a hydronium ion. So this one here is got a special name as well. It's called benzoic acid. Okay, again, the oic acid is for the carboxylic group, and then the benz part of it is really for the benzene ring. So benzoic acid is a benzene ring with a carboxyl group onto it. Now we're spending a lot more time naming here because there's more kind of nuances depending on what's going on. So I'm going to focus in on this one. This is a ball and stick drawing. Okay, all of the black circles, these are all carbons, so that would be carbon, 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 carbon. We'll notice we have a double bond here, and then all of the white circles, those are all hydrogens. So if you kind of break this one down, this is an ethene. Okay, there's two carbons, there's a double bond here, and of course this is benzene. Okay, now technically, the ethene gets priority in naming. It's more important than the benzene ring. And when it becomes more important than the benzene ring takes the name phenyl. So this is when it becomes less important than something else in the compound. In this case, the ethene is more important. So because there's only two carbons here, whichever one is attached to the benzene ring, that's carbon number 1. So I don't have to say like 1 phenyl, it's just phenyl, and then followed by ethene. This is phenylethene. This also has a common name, which I believe is styrene. From my memory, I believe this is used to make styrofoam. Okay. So that's one instance where benzene becomes phenyl. If there is a double bond, the double bond takes priority, and therefore it's called phenyl. This one here has benzene as phenyl for two different reasons, and I'm going to explain both of them. So first of all, the chain that it's attached to has 1, 2, 3, 4, 5, 6, 7 carbons. There is 6 or more carbons in a chain attached to benzene, then the benzene becomes a branch or side group. The other reason why it's called a phenyl is it's actually attached to the middle of the chain. So it's not attached to carbon number 1. This is actually attached to carbon number 2. And so when it's attached to the middle of a chain, it's going to take the phenyl prefix, and I actually also have to give this a location. So this would be 2-phenyl. So that's my branch. I've got 1, 2, 3, 4, 5, 6, 7. I got phenyl hept. That's the main chain. The main chain is all single bonds, so 2-phenyl heptane. So in terms of like testing the naming of a benzene compound in our course, The first four are kind of things that you may see, more just the first two. You probably wouldn't be asked to name these two, but definitely being shown pictures of them or asked to react to them definitely is highly possible. In terms of getting into the real nuances of when benzene is called phenyl, this really isn't a major sticking point for our course, but it may be as you proceed forward. Something else you may come across if you watch other videos online, or when you maybe take chemistry in university, the whole 1, 3, and actually numbering the carbons in a benzene really isn't something that's done too often. So we're using the most up-to-date IUPAC system for naming organic compounds. When I was in high school, I never named it this way. It was different for me. So things have changed. So I just want to talk about what one of those changes is. So if I call this spot here my reference point, and we're going to call it basically carbon number 1, most of the time when we talk about a 1,2 side group on a benzene ring, we call it ortho. I know that seems weird. So rather than saying 1, 2, you would say it's ortho. Instead of saying 1, 3, it's called meta. And for 1, 4, it's called para. So if I had a methyl group on 1 and 4, I would say they're para. If it was 1, 2, ortho, 1, 3, meta. This is not tested for our course here because we are using the new IUPAC system. And that's what I've taught you in this section here. This is the new IUPAC system for naming organic compounds. Just the reason I'm explaining the ortho meta para is if you reference older textbooks, if you watch different things online, if you go to university and you have a professor, they might start talking about this and you might think, I don't know what's going on. Or if you take IB chemistry, I believe that they still use this system when talking about benzene. So it's more of just, this is for your knowledge, but it's not going to be tested for our course. In our next section, we're going to look at drawing some benzene diagrams, and I'm actually going to start with figuring out its molecular formula. What I'm going to do first, though, is I am going to draw a benzene ring. I'm going to show the hydrogens. I'm going to actually show this with double bonds, and I'm going to explain to you how I know the basic formula for benzene. So one way of figuring out isomers is always to start with your alkane formula, which is CnH2n plus 2. Now, whenever you add a carbon-carbon double bond, you would subtract 2 hydrogens from that formula. Or anytime you make something cyclic, you would also subtract 2 hydrogens from it. Because every time you do a double bond, each carbon has to lose 1 hydrogen, so you'd subtract 2. Where the chain comes around to form a ring, the 2 carbons that meet to make the ring, they each have to lose a hydrogen to make a ring, to come together as a ring. So when I look at this, the fact that this is a ring, I would subtract 2 hydrogens from that generic formula. And then for each of the double bonds, I would have to subtract another 2 hydrogens. Now, I realize there are no double bonds, but when you average out the 1 and 1/2 bonds, you can figure it as being minus 2 for every 2 1 and 1/2 bonds, and there's 6 1 and 1/2 bonds, so it's going to be minus 2, minus 2, minus 2. So if you do that, what you get coming out is C6 H 2 times N minus 6. And this is going to tie into what we're going to do next. The reason why I zoomed out here so you can see benzene has an empirical formula of Cn 2N minus 6. So there's really not too many isomer questions on benzene because it's quite unique. So if I was to do what is the molecular formula for this compound, I would simply go, okay, dimeth, well that's 2, plus the 6 carbons in benzene. And so I would go C8, H, 2 times 8 is 16, minus 6 is going to give me a formula of C8, H10. So we're going to double check this when we do our full diagram. So C8H10. So I'm going to start with a structural diagram which shows every atom in the compound, and it shows all of the bonds. So I'm going to start with this. And I am going to use double bonds in my structural diagram just so I can follow how many bonds everything is made. Okay, so I'm going to do every second carbon. I'm going to call this first one, that looks a bit funny. I'm going to call this first one carbon number 1. I have a methyl group off of it, so 1, 2, 3. And then this one, I'm going to have a methyl group coming off of it, so 1, 2, 3. The only carbons that still need anything is this one, this one, this one, and this one. So let's start by making a mark here, and then we'll go around clockwise. So I've got a 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogens. So my molecular formula is right. Now I'm going to draw 2 line diagrams. We talked about this in cyclic. Generally, line diagrams can be done as 100% lines, or kind of a hybrid model between a condensed structural and line. So a pure line diagram here would be this. That would be a pure line diagram. And then a kind of a hybrid of that would be a condensed structural line. So then you could have CH3, CH3. And so a lot of people would just still call this a line diagram, even though you are actually adding in some carbons and hydrogens. In terms of isomers of benzene, it is very difficult to find isomers of benzene unless they can contain benzene itself. Again, the formula for benzene, generic formula for benzene is CnH2n minus 6. So it's either an isomer that contains a benzene ring itself, or it would have to have 4 multiple bonds, which is fairly unlikely. There are compounds that do have that, but it is quite strange. So you would have to have something like 4 carbon-carbon double bonds, or 2 carbon-carbon triple bonds, or some kind of combination, like 1 carbon-carbon triple bond and 2 carbon-carbon double bonds, something like that, in order to have an isomer of benzene. So it's unlikely to be tested, but we'll go through a few anyways. So let's start with this one. It says, draw 3 isomers of ethylbenzene. So if I was to draw ethylbenzene, it would look something like this. So in my opinion, the easiest thing to do would be to turn that ethyl group into 2 methyl groups, and then move the methyl groups around the ring. So for instance, you could have like a 1,2 dimethyl, or a 1,3, or a 1,4, and then you would have 3 isomers of ethylbenzene. That would be the easiest way to go about doing this. In terms of like multiple bonds, there's 8 carbons in this ethylbenzene. So I could do something like an 8 carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8. And I could put 4 double bonds on it, something like that. Or this will be a bit harder to draw. I could have, say, a triple bond. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, something like that. 1, 2, 3, 4, 5, 6, 7, 8. I don't even know if such a thing exists, but it is possible. So this would be 2 triple bonds. Here's 4 double bonds. Those are possibilities. In the next section, we're going to look at the chemical and physical properties of benzene, and they're really not any different than the rest of our hydrocarbons. So again, they're nonpolar substances, so London dispersion forces only. Essentially no solubility in water, high solubility in other compounds that are nonpolar. The only thing that would be slightly unique is out of all of the other 6 carbon hydrocarbons, it would have the highest boiling point. So if we were to compare them, it would have a higher boiling point than hexane or a hexene or a hexine or a cyclohexane. It has a higher boiling point than all of those. So benzene is used in a lot of chemical reactions, but the most commonly used reaction that benzene undergoes is a substitution reaction. So most of the time what you're doing is you're substituting off one of the hydrogens or a different substituent off of the ring for something else. Now, for the purpose for our course, we don't really allow benzene to undergo an addition reaction. It is possible to saturate benzene and turn it into cyclohexane, for instance, but we just really don't deal with that at this level. If you proceed into organic chemistry at the university level, you will be doing many different types of substitution reactions using benzene. That's really where benzene is the most effective. So let's do an example of a substitution reaction. So if I started off with benzene, we would substitute in, let's say, a halide. So if I had something like Br2, and I'm going to color code this, so I'm going to call it Br, and I'm going to add hydrogens to the outside of the benzene, even though it's a line diagram, so I'm going to add these in. What would happen is one of the hydrogens would substitute out of the benzene ring for one of the bromines, not one of the bromine atoms, but not for both of them. Remember, with substitution, we're really talking about one thing goes in, so one in, one out. So one of the BRs moves in and one of them moves out. So for instance, maybe this BR replaces this hydrogen like this, and so we end up with a benzene ring still. We just happen to have a Br there in replacement of one of the hydrogens. So I know we haven't started naming halides yet, but this would be called bromobenzene. So this would be called bromobenzene. And I do believe this is done in with iron 3 bromide as well present, but that's something that you don't need to know again quite at this level. If I wanted to substitute in 3 bromines rather than just 1, I would have to just increase the amount of bromine in the reaction. So I'm going to do this in less detail. But let's say I wanted to have a tribromobenzene with 3 bromines in it. What I would do is I'd have to have 3 Br2s in order to do that in a 1:3 ratio. So I'll stick with my color coordination here of BR in red and blue. So what I would have is 3 BRs move in, and I'm just going to separate them by the same amount of distance. I'll do like a 1, 3, 5. And I would have 3 hydrogens come out. So what you would end up having as a product would be a tribromobenzene plus you would have 3 HBRs. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.